So what we previously saw is that nuclei with high nucleon number may spontaneously decay to form more stable nuclei. So one example that would readily do that is uranium-200, and it would do so by emitting a so-called alpha particle, which is basically a helium nucleus, and what would be left over would be thorium-90. So this emission of a helium nucleus is called alpha decay. Another word for a helium nucleus is an alpha particle. And by conservation of linear momentum, if we have a stationary uranium nucleus and it emits an alpha particle, that it will have to be rebounded in another direction. Another example is beta decay, and this is done, for instance, by carbon-14. And beta particle in this case is simply an electron. So that means that a carbon turns into nitrogen, and again, there must be conservation of linear momentum. If an electron is emitted, then the carbon nucleus, or rather the remaining nitrogen nucleus, will have to rebound. And then there is what is called gamma decay, and the gamma ray is just a photon. And this may happen when a nucleus is in a higher energy state, it's in an excited state, comparable to what you know from quantum physics. And as it spontaneously de-excites, it may do so under the emission of a gamma photon, and after that it becomes a stable, or at least a more stable nucleus. So there is no change in the nuclide, doesn't change to a different element, but its energy and therefore its mass reduces a little bit. So let us now have a closer look at these three types of radiation and how we may distinguish them. One distinctive pattern is the ionization power. So an alpha particle, when it travels through air, it has a very strong ionization. It kicks out the electrons of thousands of ions in any millimeter of its path through air. Beta particles also have some ionization effect, but much smaller. And gamma rays, they hardly interact with anything, so they have very little ionization of the air around them. In terms of penetrating power, an alpha particle is easily stopped by even just a sheet of paper or by your own skin. So in that sense, alpha particles or alpha radiation is not particularly harmful unless you stand with your mouth open over an alpha source. Beta particles have a considerably stronger penetrating power. They might travel up to a meter in air, and we need a few millimeters of aluminium to stop them. Whereas gamma rays, they pass through almost everything, and they are not stopped entirely, but we might reduce the amount of gamma radiation by several centimeters of lead. And after that, there might still be some coming through. So how can we detect the different types? Well, alpha particles are positively charged, beta particles are negatively charged, and gamma rays are not charged, they are photons. So we can pass the different particles through an electric field. And then the alpha rays will be deflected in the direction of the field, the beta particles in the opposite direction, and gamma rays will not be affected at all. And since they are charged particles and they are moving, at least alpha and beta, we can get the same effect by passing the radiation through a magnetic field perpendicular to it and look at the deflection, if there is any, to determine what type of radiation we are dealing with. So the simplest way is probably to just try and stop the particles. If you have a sheet of paper or two and no radiation passes through, then it's alpha particles. If there's radiation passing through but it's stopped by a few millimeters of aluminium, then it's beta particles. Whereas if you want to protect ourselves from gamma radiation, we need several centimeters of lead, and even then we might not stop everything.